Okay, it's a long building. So today we are going to have the sixth lecture given by Frank Wilczek, and it's going to be about the quantum anomalies in QCD. So let's welcome.
Okay, so yes, last time we did, which was yesterday, we did some hard work getting to the mathematical heart of anomalies, and we also had a little bit of dessert discussing the anomaly in low dimensions, where it's easier to understand and also of independent interest now in condensed matter physics. Today, I want to return to the fundamental interactions and apply what we've learned to QCD, and this will lead directly into axions. I hope this lecture I'll get into the axion story and maybe even into the cosmology of it. This is not working. Hello? This is not the... It's not working.
Not working?
No.
Phone is not working?
No, the testing should work.
Now sharing. Try this.
Okay, good. So this is a tremendous triumph of QCD, of quantum field theory and our understanding of nature. And at the same time as it's a triumph, it also poses a next level of questions that seems to be very promising as to expand our understanding of the world, in particular to provide the dark matter. So we've discussed how anomalies can remove symmetries from theories. And in the case of pi 0 goes to 2 gamma, that was a desirable result. And there's another outstanding example of it that's going to be central to our story going forward. That has to do with UA1, which is the axial baryon number symmetry that QCD has in the limit when the quark masses are 0. In fact, they're very small, so this is an approximate symmetry. Furthermore, it's spontaneously broken, as we'll discuss, but the fact that the underlying theory had this symmetry at the classical level was potentially a big problem. And so the fact that the anomaly rescues the situation is quite important. So here's the more detailed version of those words. In the approximation that we neglect the mass of the up quarks and the mass of the down quarks, remember mass terms connect left to right-handed components of the field, or fermions. But in the approximation that the dark masses are 0, then at the classical level, if you just look at the Lagrangian, we have a symmetry that allows you to transform the up quark fields and the down quark fields into each other. Okay. We're neglecting the fact that they have different charge because it's just electric charge because it's just QCD. We're neglecting also the weak interactions, neglect all that. Those are comparatively small effects relative to the strong interaction. Then we have a what's called chiral flavor symmetry, which is U2 cross U2. We can make arbitrary phase rotations and unitary transformations separately on the left and right-handed components of two fields. They both, of course, are color triplets. Okay. So breaking that down a little bit, the U2 is U1 cross SU2. And one of these symmetries is very familiar. That's baryon number symmetry. We take the symmetry which rotates both left and right quarks in the same sense. And then there's the complement to that, U1A, which rotates left and the opposite way to the right for both flavors. And then there's the isospin symmetries, which rotate U into D, SU2. The vector version of that, where we rotate both the left and right together, is conventional isospin, but there are also axial versions of those transformations. Okay. Now, in QCD, we have spontaneous symmetry breaking, so-called chiral symmetry breaking. This is a dynamical phenomenon that says that in the ground state, in vacuum, the left and right-handed components condense. So this is an older version of what may now be more familiar of a Higgs field condensing, but this is a dynamical version that you don't have to put in a scalar field and postulate interactions. Just the interactions of QCD itself spontaneously make these correlations exist. So you can think of these as mesons that want to form, so quark-anti-quark pairs, and they're so strongly bound that their mass is negative, so they fill the vacuum until they start to repel one another, and then they form. They're only at a finite density. Very rough picture, but that's the spirit of the thing. When this idea was introduced, and that actually predates QCD itself, goes back to thinking about just isospin and low energy strong interactions. But when it was first introduced by Nambu, and basically he got the Nobel Prize for this line of work, it was a clever hypothesis about what might happen. Now it's a computed fact. Now we have QCD, and we can just compute to see if these condensates form, and they do, using supercomputers, actually solving the equations. So this now the vacuum with these correlations in it has less symmetry. Now it's not possible to rotate the left and right-handed pieces separately and leave the ground state invariant. Okay, so what happens then in terms of the symmetry breaking is that we have the SU2 cross SU2, which was separate rotations of left and right-handed fields, breaks down to just the diagonal transformation where we rotate them both in the same way. That leaves these invariant, these correlations invariant, so it leaves the ground state invariant. That's not broken, but the symmetry has been reduced. Now, when you reduce a symmetry, that has consequences. When you spontaneously reduce a symmetry, this is the lesson of the magnet and the magnetic compass. So in a magnet, we know now, they didn't know then, but now we know, is you have spins being aligned spontaneously. So the spins have no preferred direction individually, but they want to have the same direction as their neighbors, and that can lead to long phase transitions and long-range correlations. Then that breaks the symmetry. They all choose one. They have to choose one direction if they're all going to be doing the same thing as their neighbors, and so that they choose it, and that's how we understand the origin of ferromagnetism. Now, if you have that phenomena, all the spins in your sample have agreed on a direction, And so if you make local perturbations to it, you're not going to disturb that long-range order. However, if you disturb all of them, or if you make very long wavelength disturbances, then without very much injection of energy, they will be able to move coherently in the direction that was the original symmetry direction. Okay. That's the line of thought that leads to what are called Nambu-Goldstone bosons, that whenever you have spontaneous symmetry breaking, there are long wavelength, low energy excitations. And in this context, those low energy excitations that correspond to moving in the broken symmetry directions are identified with the pi mesons. The puzzle that Nambu was trying to address in those early ideas was the fact that pi mesons are so much lighter than the other strongly interacting particles. And he said that maybe they have to do with spontaneously broken symmetry. Okay, of course, in the case of the magnet and the compass, the fact that a magnetic field can move the spins all coherently is the essence of how a magnetic compass works. Okay? And yet it's robust against most perturbations. So local perturbations. Okay, now that's fine. That was a triumph of theoretical insight. But there's also a problem in the context of QCD, because there's another symmetry that gets broken by the condensate. Besides the SU2, there was the U1 symmetry with a common phase, and you can have the axial U1, UA1, is when you rotate both the left and the right-handed, both the left-handed U quark and the left-handed D quark in the same direction, and then the right-handed versions in the opposite direction. Okay, so it's baryon number, but acting in opposite directions on left and right, so it's axial baryon number. In this case, there's no pion, there's no analog of the pion, there's no particle that has zero isospin, it's the U1, and is light like the pions. So there's no such beast. So something is missing. Okay, the particle, the light particle that should accompany this formation of a condensate, if you believed in the classical theory, the symmetries of the classical theory, doesn't exist. Okay. In all this discussion, I've neglected the existence of quarks besides the U and D quarks, and also the fact that the quarks do have small masses, but if you do that more carefully, it doesn't really improve the situation. Those are small effects within the world of low energy QCD. Okay, so we've got a problem. If QCD is going to describe the world, we have to understand why that particle doesn't exist, the Nambu-Goldstone boson of spontaneously broken axial baryon number. Well, we've learned that sometimes symmetries are fake. Symmetries of the classical theory don't survive quantization. And we worked quite hard to understand that. And we saw that you could nail it down, nail one important form of such symmetry breaking through quantization down by just considering triangle graphs. That captured a lot of the structure. And here, remember we had this phenomena with an abstract fermion. massless fermion. We put it into a triangle graph and computed the divergence of the axial current. In our original case, we looked at the vertex where it goes into 2 photons, but we can also do the same thing with 2 gluons. The couplings are basically very, very similar, just with extra indices for colors. And you get the same sort of result now that the divergence of this axial current, which classically is 0, because to define the theory, you have to regulate, and in the regulation, you necessarily violate this symmetry. You find a right-hand side, which is of this E dot B form. Okay, exactly. So a first reaction to this, which people had historically, briefly, was, so what? So you don't have violation of that conserved current, but there's another conserved current, because as we've mentioned several times, these E dot B type terms are actually total derivatives. Okay. So you can write it this way, and then that means you can define a conserved current by actually subtracting off the K mu. So there should be a minus sign, but you get the idea that there's a modified current that still means that there's a modified conservation law that's spontaneously broken, and you're back in the soup. But as we learned also, this K mu is a very formal argument, and the K mu that's involved here is not gauge invariant, and so it might be singular. Okay. And in fact, we had a very specific mechanism for that. You can have field configurations with finite weight, which basically translates into finite trace of E squared plus B squared, where, however, the surface terms that are involved in K, so the surface terms that feed into E dot B, do not survive even when the surface gets very small. They're singular. Okay. So that can happen. Well, the fact that this is finite means that G mu nu is not singular. And in empty space, G mu nu goes to 0 would mean that it's a gauge it's locally a gauge it's a gauge transformation, and that's true locally. It's not necessarily true globally, and you have the possibility of cancellations between d mu and a mu a nu, which will take different forms in different gauges, but you can never make them go away entirely, and that's how you can pick up surface terms in these integrals. Okay. So there's a long and interesting to mathematicians story about this that goes by the name of finding instanton solutions. If you want to see examples of this phenomena in concrete field configurations. But I will skip it because actually the approximations of using classical field configurations in these functional integrals is not really adequate within QCD, where this coupling isn't small, and so the fluctuations are very large. However, we can draw some conclusions from these mathematical considerations that do hold up in the full theory. That is that indeed you do get non-trivial contributions that are of a topological nature. So values which are quantized. They represent topological invariance. They're related to what's called the Chern number of these fields. That means that you have this theta term, this potential interaction, which is problematic because it violates time reversal symmetry, actually does contribute to the physics. It's classically it doesn't because it's a total derivative, but quantum mechanically it does. We're happy that it does because it removes the U1 asymmetry that was causing problems, but we're disturbed that it does because it violates time reversal symmetry, and we don't want that. So we want the physical effect, but we don't want the physical coupling to be part of the theory. Okay, so we've involved in this argument quite a few complex concepts, so it may be welcome to have a visual reminder of the main structure and the main conclusion that is easy to remember. So we connected also this phenomenon of field topology to the existence of zero modes. Remember this, the Atiyah-Singer index theorem. We evaluated it on the one hand using modes of the Dirac operator, on the other hand, the singularity structure and relating it to the integral of FF dual. So the integral of FF dual counts the number of left-handed minus right-handed zero energy solutions. So there are zero energy solutions, but the functional integral when you integrate over fermion fields is a determinant, so you just get zero. To get a non-zero result, you have to include some sources that occupy the zero energy modes. So I won't go into the technicalities. We've had enough pain of that kind recently. But I hope that this makes it plausible that we get out of all this, the end result is that we find that in QCD, in the standard model, if we analyze non-perturbatively, there's an interaction that you don't see in perturbation theory that comes in when you have topologically non-trivial fields. So unlike the basic interactions, which are point-like vertices, should be thought of as a cloud, which comes about when the field has topological structure. And have one of these clouds, when you have a place where the field has a topological structure, so you can think of it as a vortex or a hurricane in the field, you have a coefficient, which is e to the I theta. That's for the basic topology. You could have several of them where you could have the anti-topologies, in which case you'd have e to the n theta or e to the minus I theta. But if you have the basic so-called, the basic topology, so the integral of FF dual is 16 pi squared times 1, then you get e to the I theta. And because of the zero mode structure, which has to have left-handed fields and right-handed fields that count the contribution to the anomaly, you get one each of every species of left-handed arc coming in to this effective vertex, and one copy of the right-handed version on coming out. And this sort of been very reminiscent of how pair production in the 1+1 dimensional theory violates chiral symmetry. In that case, you violate the baryonic chiral symmetry these are all organized into a flavor singlet, so you don't violate any of the isospin or other flavor symmetries other than overall baryon number. So this is what's called the 't Hooft vertex, and is a user-friendly summary of the additional thing brought into the standard model by careful consideration of anomalies. Okay, and it's very good for removing the fact that there are these interactions without the coefficient e to the I theta, just populating the vacuum in pairs. That removes the U1 symmetry, so that's good. But the fact that they might occur in the basic Lagrangian with a non-zero coefficient that violates time reversal, that's really bad. So T is for trouble. This is basically summarizing where all this analysis has left us. So looking at this vertex, we see that we can't remove the overall phase of the quark mass matrix, which was part of our procedure in analyzing, in getting a canonical form for the standard model Lagrangian. We can't, and because this is sensitive to a phase of overall quark mass matrix, and we can't remove the theta term of QCD because this emergent interaction, this non-perturbative interaction, is potential non-perturbative interaction. It does depend on theta. We can, however, rotate one into the other. If we make a rotation on all the quark phases in that vertex, that's equivalent to changing the coefficient of theta, the value of theta. Right? So we can shuffle from one into the other. Now, that interaction is very, very dangerous phenomenologically. This is what the fact that it violates time reversal, but doesn't violate any other quantum numbers, means that it can contribute directly to processes that don't violate any quantum numbers, but do violate time reversal, such as the existence of an electric dipole moment for a neutron. And sure enough, if you calculate the contribution that you get from this kind of term to, this is a primary interaction, the gluons of QCD, so it's very important for the neutron structure, you get phenomenologically a bound of 10 to the minus 10. So this is something that's very striking, a very, very small number arising from nowhere, and we would like to have a qualitative explanation of why it happens. Now, one thing that's sometimes suggested in similar problems is the so-called anthropic principle, that if some parameter, especially, for instance, the density of dark energy, was different, it would make it very difficult for life to thrive. And so the fact that we observe, we are alive, capable of observing the situation, forces the parameter to be very, very small. But that doesn't apply here at all, because you can convince yourself easily that if the theta parameter were 10 to the minus 10th, for instance, 10 to the minus 1, I'm sorry, so 1/10, it would have negligible effects on anything practical. So it's not required anthropically. So that, you don't have that stupid argument. Okay, so the grand conclusion of all this, is that the idea that fundamental time reversal violation arises solely due to a complex phase in the weak currents that couple to W plus and minus, which appeared in our analysis of the structure of the standard model, is remarkably successful, but it begs a question, because there was another interaction that could have been in the world that was forbidden by T, not by any other general principles, and it happens to be very small in the world. So the story of T violation, of why there's a small but non-zero T violation in the world, is not quite complete. We need to understand why the theta term of QCD is so small. And that's sort of, now we've filled it, now we've done this diagram. Okay. And we're left with, looking at the world, we see this, an improbable balancing act that effects that could have violated time reversal, in fact, don't. We have time reversal in the world, but somehow it doesn't leak into the theta term or the quark mass matrix. If you saw this on a beach and someone asked you if it's a coincidence, you'd say, no, probably not. Probably. So we're going, and the burden of our next discussion is going to be to have a rational explanation of why the theta term is so small. And as you'll see, the most compelling explanation that's known by far at present has important consequences that can be checked experimentally and could very well explain a lot about the universe. Could be most of the matter described coming out of QCD is the dark matter. Okay, so that now leads into part 3, where we try to address this issue. Okay, so we go back to our analysis of the symmetry structure of the standard model. We revisit it now with a bit more sophistication, because we know there's a non-perturbative interaction that we have to worry about, in addition to the classical ones. So if we go back to the minimal standard model, we had, remember, a Higgs field phi that's giving mass to the quarks. So we're looking at this part of the standard model. There are other parts, but this is the crucial thing for our purpose, is the quark masses. And they came from, this was the left-handed up and down fields. Remember, there are it has 3 favorite components. That's the J. It also has 2 weak interaction components there. I've suppressed the color indices, but I wanted to show those 2 because the coupling to the Higgs field is important, and we need to spell it out a little, and the flavors are certainly important. Okay, so that's the form of the coupling. That is the most general form consistent with all the general principles. The hypercharges match up. Remember, the hypercharge of the average charge of the Higgs doublet was -1/2. This is -1/6. And this is, so the average charge of the left-handed quarks, there's 2/3 and -1/3, and then you do the antiparticles, so it's -1/6, and this is 2/3. So it all adds up to 0, which is what you want for an invariant interaction. Okay. And then the weak indices match up. This is why you introduce a Higgs field with the exact quantum numbers that you do, so that you can make this happen. And introducing just one doublet is sufficient to give masses both to the up-type quarks, U, C, up quark, charm quark, and top quark, and also to the down-type quarks. That's maybe not completely obvious, but if you take the complex conjugate of the Higgs field in its primary form, the hypercharge is minus because it's a complex conjugate, and it's still a doublet under SU2. And because it's SU2, the weak interaction, you can hook up, you can form a singlet not only in this way, but also using the epsilon symbol, like that, the two-dimensional antisymmetric tensor. So the same Higgs field can give masses to both kinds of quarks. Okay. So that's that, and that's how the standard model, the minimal standard model, works. And now we know that the Higgs field does seem to be pretty minimal, so this is actually what we have. We're also, however, going to consider a variant where we have two Higgs fields, and we don't use the complex conjugate. And you'll see why it's important to consider this variant. Okay. Now, in the minimal version, if we refer to the Heft vertex, I hope I have the picture here. Nope. Okay. The overall phase of the quark mass matrix, so its determinant, is a definite function of G and H. Okay. You can rearrange the fields and change their phases and stuff, but you don't change the determinant. And the Higgs couplings, the vacuum expectations, that values that occur, are 3 copies of V and 3 copies of V star to get the quark masses. So the phase of the phi field cancels. Okay. So the phase of the quark mass matrix is fixed by the basic parameters of the theory. It's not a dynamic variable. So you have your primary theta term and your primary quark mass matrix phase. It's encoded in this complicated way, but at the end of the day is a fixed function of the primary parameters. And so this leaves the smallness of the net theta term, the difference between those two phases, totally mysterious. Okay, so you can't redefine things in such a way as to naturally explain why the overall phase of that Hooft vertex is small. However, in the variant model, that phase becomes a dynamical variable. Because the Higgs, we have separate phases for phi 1 and phi 2. One of them couples to the down type quarks, the other to the up type right-handed quarks. And so that phase, that dangerous phase that's causing us so much trouble, the net phase of the quark mass matrix that arises from the Hooft vertex, is a dynamical variable. And if it's a dynamical variable, that opens up the possibility that evolution variable settles down to a small value, and in that way explain why it's observed to be small in the world. Okay, so that's the basic idea. Let's see how it is embodied in a model. So this was the original axion model, the weak scale axion model. So you see it's very simple to make theta into a dynamical variable in this way. It's the relative phase of two condensates, which can form independently. But we want to make sure not only that it's a dynamical variable, but that it wants to settle down to where we want it to zero. And we want to do that in a way that's not ugly. Okay. So that means we want the energy of this phase to be primarily determined by the value of that effective interaction. We want it to be primarily associated with that effective theta term, and we want it to have its energy minimum where the theta term is very, very small. So the way to do that is called Peccei-Quinn symmetry. It was developed by Roberto Peccei and Helen Quinn. And it's the hypothesis, this symmetry, is a symmetry of the classical theory that's broken by quantum mechanics. But that's what you have to do. And it says that the theory should be invariant under simultaneous rotations of phi 1 and phi 2, those two Higgs fields that we've introduced. That has some teeth in it, that assumption, because it forbids interactions that would otherwise be allowed. These are both doublets, and we saw that by using epsilon symbols and things like that, you can make two doublets couple in a singlet way, in an invariant way, either with phi 1, phi 2, or phi 1, phi 2 squared, and both of those would violate this symmetry. And in both cases, you would have an energy that has nothing to do with the 't Hooft vertex, that depends on the overall phase of these guys, and therefore would prevent us from having an energy that's responsive primarily to the phase of the 't Hooft vertex, because it's the effective theta. Okay, so now let's go to the picture and see how, despite that classical symmetry, that classical Peccei-Quinn symmetry, the quantum theory, because of the anomaly, which then is reflected in the 't Hooft vertex, how that breaks the symmetry and makes the energy density of empty space depend on the value of the effective theta parameters. Okay? And it's exactly this. You have all the remember you had the left-handed quarks coming in and the right-handed quarks going out of this 't Hooft vertex. The up-type quarks are getting their mass from phi 1, so there are 3 of those. The down type quarks are getting their mass from phi 2. There are 3 of those. And there's an overall e to the I theta. So this gives an energy that goes like the effective value of the overall interaction, including both quark masses and theta term. So we call that alpha, the net phase of this whole thing. It's cosine alpha because we also have the anti version of this, the parity and time reversal conjugate of the field topology and everything. So that's minus cosine alpha. The minus sign requires a little bit of a calculation, but otherwise the form is got to be this. And then it's associated with typical QCD scales. There's nothing particularly small about it. You have quark masses after the condensation and gluon interactions. So it's the scale, rough, dimensionally, it's the scale of QCD to the fourth power. So 100 MeV or something to the fourth power. And there exist more precise lattice gauge theory calculations, which we'll allude to, but that they bear this out. So if you, in this model then, the phase that multiplies the 't Hooft vertex in vacuum is exactly what appears in the energy. And the energy is indeed minimized at the symmetry point where the effective theta term is 0. Yay! Yeah, so that. Okay, you could have guessed a priori that the 0 point would either be a local minimum or a local maximum because that's the nature of symmetry points. But here it's a local. Okay, so that's a basic model, the original model that solves this problem formally. We'll see that it has phenomenological problems when you examine it in detail if you use the Higgs fields that violate the weak interaction symmetry. They can't have too large a vacuum expectation value, and that leads to problems, but that leads to the axion being too strongly coupled. But let's not get ahead of ourselves too much. Okay, so we want to generalize this model for later purposes. Now, originally, this was back in the mid-1970s. The standard model was nowhere near as well established as it is now. And thinking about unification, some of us thought was premature. So we didn't think about scales beyond the weak scale for symmetry breaking. But now that's very routine. And we could ask, is it possible? Here we broke the Peccei-Quinn symmetry using Higgs-like fields, so SU2 doublets that violate the weak interaction symmetry, but could it be broken instead at a much larger scale? We don't want Higgs doublets for that purpose, because if we did that, it would violate, we give the W bosons enormous mass, as well as the quark, so we don't want to do that. Actually, we can construct very simple models of ultra-high energy physics that do the job. So, for instance, we can introduce a standard model scalar complex field, call it rho. So it's a singlet under SU3 and SU2 gauge groups of the standard model. So no covariant derivatives in it, if you like. And suppose it transforms non-trivially under the Peccei-Quinn. We're going to define our Peccei-Quinn symmetry so that this field transforms non-trivially and requires a large vacuum excitation value. So the Peccei-Quinn symmetry is exact classically, spoiled quantum mechanically, easily broken by a lot. That's the global picture. And finally, to make this connect with the theta parameter of QCD, even though this field is a singlet, do the following. So we want to bring in this scalar field coupling to the 't Hooft vertex. So there needs to be some quark that it couples to. It's going to get a big vacuum expectation value, so we don't want that quark to be any of the low energy quarks. So we We have a very high energy, very massive quark, and that quark is getting its mass just from the interaction with the rho field. So the rho field is kind of like a Higgs particle, but it's a singlet under all the strong, all the interactions of the standard model, and it's the source for a mass of a quark, heavy because of this interaction. When rho gets a large vacuum exploitation value. So in that sense, in that way, because it connects left to right-handed quarks because of the zero modes, the rho field, the phase of the rho field is precisely the dynamical degree of freedom whose motion changes the effective value of the theta term, but doesn't change anything else, right? Because of the symmetry. The only place the symmetry is broken is in the 't Hooft vertex, and so that dynamical degree of freedom does what we want. It makes the theta term, in a sense, a dynamical degree of freedom that wants to settle down to a very small value. So many variants of this basic idea are possible, and they all predict a similar mass, a similar pattern of, at last the hero or heroine of the story makes an appearance, the axion. The phase of this quantum field now, so what used to be theta is now a quantum field. The phase is the axion. It's something that that the energy only depends a little bit on, because it's the energy associated with the 't Hooft vertex. And so there's a new kind of particle that comes out of solving this difficulty with the foundations of our understanding of time reversal symmetry. And we can say quite a lot about it, because it's introduced to do a very specific job, and it has to do it in a more or less unique way. So if we had a global symmetry, I'll write the equations on the next slide, but articulating again the lesson of the magnetic compass, if we have a global symmetry that's spontaneously broken, we can expect to get low energy excitations that correspond to restoration of the symmetry. If we have field excitations of low frequency in space and time, so it is that couples gradiently to the overall symmetry breaking thing. If you do change globally the phase, this thing will couple to it. And the strength of the coupling is inversely proportional to the scale of symmetry breaking. That may not be completely obvious, but let's write equations from which these properties can be immediately derived. I'll wait for the ding dong. Okay. All right. So we imagine we have some order parameter or scalar field that transforms under a symmetry and breaks the symmetry because it gets a vacuum a non-zero value in vacuum. Then if we consider the Lagrangian for that field, we'll have its kinetic energy, but also and its interactions. And its interactions, because it's associated with a symmetry, according to Noether's theorem, which we discussed a little bit before, and I won't go back, but just as an exercise, you can show that. I'll ask you to show that this is how things change if we change this phase in a space-dependent way or space-time dependent way. If we changed it in a space-time independent way, because it's a symmetry, nothing changes. But if we change it with a gradient, we pick up this kind of structure. That's how you prove Noether's theorem. Okay, so that's arising directly from the fact that it's a symmetry, and then it gets a vacuum expectation value. This turns into a kinetic energy kind of thing, gradient, but not normalized. It has the scale of the symmetry breaking outside. So if we normalize the field, so it looks like the coupling is inversely proportional to the scale as claimed, and it has a very, very specific form that's tied to the symmetry. So when we have a particle like this that's attached to a symmetry, we get a very specific kind of picture of what its interactions are going to be. And if it's associated with an anomalous symmetry, we know the form of the anomaly, we also get a very specific picture of what its interactions are going to be. And that's the case for the axion. So that gives rise to a non-zero mass. See, it's very small, but non-zero, and to non-derivative couplings, which are very small also, but not zero. So here's the vertex. Now, the mass term would be associated with quadratic variations around the minimum. The minimum was like that, so we get quadratic variation. So there is a mass term. It's got QCD to the fourth in front, and then we get a 1 over f squared from the fact that we have to renormalize the phase to get a properly normalized scalar field, kinetic energy. Okay. So the mass of the axion squared will be lambda q of order lambda QCD to the fourth over f squared. That's the mass squared. Yeah. And then all the other equations follow from the derivative from the interaction with the Noether current, derivative interactions with the Noether current. I won't spell out the derivations, but this is what it looks like at the end of the day. I've actually taken the derivative from here and applied it to the current, so it looks a little bit different, but this is the form that it takes. And each of these terms has a significant meaning, which I should spell out. Which I think I labeled them. Yeah. This, and the C's, by the way, the C's and the D's here are numbers of order unity that can vary depending on the precise details of how you implement the Peccei-Quinn symmetry, whether you give some extra fields non-zero charge or not. Okay, so that affects what the current is and therefore what the coupling is. But those are all effects of order unity. The qualitative pattern is universal. So this term reflects directly the fact that changing the axion field changes the value of theta. If you like, this was the reason for being of the axion field. So there it is. We also have an anomaly in general in the electromagnetic current, in the electromagnetic coupling, a two-photon coupling of the axion, because the quarks are electrically charged as well. And that gives rise, this term gives rise to a very, very interesting subject that also is very important for the experiments of to detect axions, but also very beautiful equations that have found utility in condensed matter physics, the axion electrodynamics. And then there are these Yukawa couplings, very much like the original coupling that Yukawa postulated between pi mesons and nucleons in the prehistory of the strong interaction theory, if you like. But it has that structure. And this corresponds to actually giving, that corresponds to adjustments of the quark masses, which we saw. And if we throw in rotations of the lepton fields, we also get that. So that's the axion, which cleans up a problem with an axial current, and some madman named it after a laundry detergent. So we'll be discussing in some detail the cosmology and the experimental search for the axion, but let's first survey the landscape to give context. So we have a new particle that's very light by particle physics standards. We're going to be dealing with F values. You'll see why momentarily. We're going to be dealing with values of that F, which is remember the symmetry breaking scale, of order 10 to the 10th GeV and above. So much, much larger than the weak scale or the usual scales of particle physics. That means that the mass, which is lambda QCD squared over that symmetry breaking scale, is going to be quite small by particle physics standards. As fractions, generally very small fractions of an electron volt. And its couplings will be inversely proportional to F, so very weak. So it has a very unusual phenomenological profile. The fact that it's light means that it can be produced easily. There's no energetic barrier, but the coupling is very small. Now, you have a somewhat similar situation for neutrinos, and that's very important for the theory of stellar evolution. You produce neutrinos and they escape, and that affects the energy budget of the stars, and it's a drastic effect on their evolution. Axions would also drain energy from stars in new ways. It's one effect that you might look for. And axions can allow light to shine through walls. You have this axion coupling to the photons, which remember was E dot B, so it's a quadratic coupling, which means that in the presence of a magnetic field, for instance, an axion can convert into a photon. So if an axion, you expose it to a magnetic field, which could be a magnetic field or it could be just inside matter, you could exploit the matter couplings. So you plow a photon beam into a wall, and sometimes a little bit of it will convert into axions, which then can travel a long way without interacting. Then you put another wall, let them interact, and maybe turn back into photons. So this is the light shining through walls experiment. And that's one way to search for axions. That's not trivial at all. And in fact, there are plans to do this kind of thing at TDLI with powerful lasers. Axions can also help rotating black holes to spin down. Okay. axion coupling is weak, but the gravitational coupling is even weaker. So if you have a competing source of energy loss, that can affect the theoretical predictions for how black holes evolve. And that's an interesting story. The sun can emit axions. So you can point some kind of detector at the sun and see if there's an extra energy being radiated, even if it's very small, you can look. And then finally, what will turn out to be most important, axions are produced abundantly in the Big Bang. I think will be the most important. None of all these are interesting. But people have thought a lot about axions, and and put a lot of work into trying to detect them. So it's not just me that's on this bandwagon. This is a sort of exclusion plot. On the x-axis is the mass of the axion. It's a one-parameter theory because of the value of f is not known theoretically. And but once you know that, you have a pretty good idea of the couplings. And so on this axis, you have the axion to two photon coupling. So basically the coefficient of A E dot B. I won't try to be more precise, but the one parameter theory links those together and is represented by this golden band here. So you have, once you know the mass, you will coupling pretty well. And many different kinds of experiments and observations have been used to constrain the axions. But you see there's a very robust phase space here of allowed couplings. And for reasons that clear, particular region is particularly important to explore. This is where axions provide the dark matter, and people have been working hard to test that hypothesis. I'll be saying quite a bit more about that. It's definitely not a finished story, but it's at a crucial junction these days. Just to show you how big the efforts are that people have put into this, this is a proposed and I think actually being constructed object at CERN. This is a Norwegian physicist, so quite tall. And you see, this is a gigantic thing that's meant to point at the sun. It has to be movable. And it's filled with a gigantic magnetic field. And the idea is that axions coming from the sun will convert in that magnetic field into X-rays, which then you detect at the end. This is called the EAXO project. If we go back, an existing version of that experiment is called CAST, and that's here. The EAXO will push this down quite a bit. Okay, so the next subject is axion cosmology. I think, however, in view of the time, maybe I should not attempt to go too far with that. Well, I'll make a start. We'll make a start, because otherwise we're never gonna. I should mention, okay, originally you see these numbers here, we're on number 9. I have 20 installments. The next few are about axions, but then I was planning to talk about axions, not T-violation in matter and then biology. I obviously will not be able to do that. However, I will continue this series in electronic form at MIT and finish it. So that will make that available in a few weeks. And in real time, and then online in a few weeks. Okay, so here's the picture of axion cosmology. We have a scalar field like that rho field that has a magnitude and a phase. Okay. The magnitude is going to be fixed by the spontaneous symmetry breaking, and then the phase is basically the axion field. We want to put this, though, in the context of cosmology. We want to put it in the context of reality. Okay. And because the axion couplings are so weak and it's so unusual, it's not obvious that it settles down to the ground state rigorously. In fact, you'll see that it doesn't, and it's very important that it doesn't. But what you expect cosmologically is you have, of course, you have a field, so it fills all space, but we're just going to look at one representative point in its internal space, and this is the internal space is a magnitude and a phase, and it has, as a function of that magnitude and phase, you have energy. In the early universe, you start up somewhere, and because the early universe is hot, it's going to have random values at some level, and then condense, and then start rolling down because it'll seek the minimum energy as the temperature becomes less important. It'll try to settle down. So that's the picture. There's a phase transition at a very high scale, so that will occur early in the history of the universe at a high temperature. And at that point, this field, which we called rho before, somehow now it changed to phi, gets a vacuum value and a phase, and that's essentially the axion field. We will show next time that this stores energy due to the missile, well, we showed it already actually, that it stores energy proportional to f sine squared theta 0 if it's away from its minimum. As time goes on, we will show that this order parameter field settles down close to the bottom of the well, but there are residual oscillations in the phase. So the phase is very weakly coupled because the symmetry breaking scale is very large. There are residual oscillations in the phase. They're very small in numerical magnitude. So the axion, its job, the effective theta term is very, very small, but it's oscillating around the minimum with some amplitude. Because it's so stiff, even very small oscillations can represent a lot of energy. And these residual oscillations can be considered as a collection of particles. In fact, if you look at the details, it's sort of the world's ultimate Bose-Einstein condensate. It's a classical field that's coherent, that oscillates. And if you interpret that field as particles, it's the collection of the field quanta that's the cosmic axion background. Okay, in the later evolution of the universe, the coherent condensate is broken up by interactions and gravity and differential motion, so it doesn't stay coherent. It produces a lot of particles. And one can predict what the energy in this fluid is. And okay, so this is what we're going to do next time. We'll derive this more quantitatively. Let me find a nice place to reach a thumping conclusion. Well, let me find a nice thing to stop on. Okay. Oh, here's a good one. Okay. So we will soon be showing that with appropriate choice of the F value, the scalar symmetry breaking, this axion background, this energy stored in the residual oscillations of the theta determining field, provides the dark matter of the universe. So this is where you get exactly the right amount. You get a little bit less than the right amount over here, so that's perfectly fine. You get more over here, that's less fine. And you see that if the axions exist at all, they have to contribute significantly to the dark matter of the universe. It goes like, 1 over F. So within a factor of 100 or 1,000, it has to be an important contribution to the dark matter. So why not most of it? And if it's most of it, that's where you have to look. And then we'll discuss how the prospects for doing that are. The prospects are looking very good. So that's I think, an appropriate place to stop.
Okay.
I hope that whets your appetite.
Okay, thanks, Frank. Now it's open to question. Any question for students? Axions.
Yeah,
Jiao
this one.
Hi, Frank.
Hello.
Maybe I have a question about U1 symmetry in superconductors.
Okay.
So we know that U1 symmetry is spontaneously broken in superconductors,
Yes.
and people say that there's no non-Goldstone bosons in superconductor, and the explanation is like this non-Goldstone boson is eaten by the gauge field. So I'm quite I don't quite understand about this explanation. So
yeah, okay. In that derivation of the Nambu-Goldstone boson, you started with a kinetic energy term for the scalar field that got a vacuum that had a phase and a magnitude, and the phase was the Nambu-Goldstone boson. And when you reduce the kinetic energy term by expanding around the condensate value, so you put the big scalar field phi equal to F times e to the I A, where A is going to be the Nambu-Goldstone field, you get the canonical kinetic energy for a scalar particle. Now, but if that scalar particle is coupled to a gauge field, then you don't have just the derivative, you have the covariant derivative. And that changes things. For one thing, you have condensate squared times vector potential squared. So you get a mass of the photon. And then if you analyze carefully, you see that you actually don't have a massless scalar field anymore. It's gone. So it's the fact that you modify the analysis by including covariant derivatives. That's really all there is to it.
So the key point is the covariance derivative.
Yes, the coupling is, or in other words, that's the coupling to the electromagnetic field, and that makes all the difference. Yeah.
Okay, thank you.
Right.
Hi,
Yes.
Frank. I'm Shaofeng from TDI. Very nice lecture on axion physics. I have one comment and one question. For the comment, I guess the T is not the trouble. T violation is the trouble. So I guess probably it's better to use.
We've talked about, we mentioned this several times. If time reversal symmetry were an exact feature of the physical world, that would be lovely, and we'd have nothing to. It's not clear that we could go deeper. That's a beautiful principle that could have been a primary principle of physics. But the idea that T is violated a little bit, that is not satisfactory as a primary hypothesis of physics. That's something that we really want to derive.
I see.
From more beautiful and profound principles.
And my question is about the 12th vertex.
Yes.
Is there any intuitive way to understand how this vertex appears?
No.
No. Okay.
That's why we went. I hope not. I don't think so. And no, it shouldn't be. It refers to field topology for one thing, and massless fermions for another. And it's it took me a full lecture and even a little bit more to even do a not fully rigorous analysis of it. Leads to it. I tried to give an honest introduction, and I don't know how to make it any simpler.
So yes, purely is a topological effect.
What's that?
Yes, purely is a topological effect.
It rises as a consequence of the fact that gauge fields can have non-trivial topology as a very specific kind that's connected to the existence of zero modes in fermion fields.
Okay, thanks.
Okay, any more questions? Xunxiao?
Yeah.
Hello, Frank. I have several questions. Maybe you cannot. Maybe there is not enough time to explain all
Well,
of them.
let's try. Start with the most important.
The first question is, you mentioned that this axion has a mass of 10 to the minus 4 eV, and it's almost.
Well, it's depends on the value of f, but 10 to the minus 4 is a
okay. Let's say it's 10 to the
reasonable
minus
mass.
4 eV is almost the same mass as a neutrino. Then its speed would be about equal to the speed of light. And then it cannot be the cold dark matter.
Oh, no. Well, it depends how it's produced. In the so neutrinos are produced basically by thermal processes in the early universe. The axion is very different. It's produced as a classical field, and it's actually is produced very, very cold. The field is very uniform, which means the gradients are small, and so if you interpret it as particles, it's very cold. So axions are definitely cold dark matter.
Okay. Yeah. And the second question is, since we cannot define left and right by either mathematics or physics, but left and right, they do behave differently in weak interactions.
Yes.
So shall we define left and right by weak interactions?
Yes.
So that's a little.
So the asymmetry between left and right in fundamental physics was a suggestion. Well, was a theoretical suggestion by Li and Yang based on analysis of certain experiments, and then other experiments verified it and led to a rich, successful theory, and was a very important ingredient in discovering the standard model, where it's now firmly embedded as the base, a very basic principle of how the weak interactions work.
Yeah, but how do we define left and right?
We define left and right by those equations.
Okay.
Ultimately, I like to say sometimes, ask my students, what is an electron, for instance?
Okay.
And the answer is an electron is something that satisfies the equations for electrons. That's what it is. You can't define it in that's the ultimate definition. And from that, you get all the observed properties of electrons.
Okay.
And then it's the same answer for what is a photon, what is an axion, what is left, what is right. We have great equations that are derived from profound principles that have been verified in many, many precise applications. And so we should trust them. Yeah.
Okay.
Yeah.
And then the third question is, we know that in four-dimensional world, there's no theta term. Then it would be quite convenient to just...
Come again? In what?
In four-dimensional universe, there's
You
no
mean
theta
if
term.
there are 4 space dimensions.
Yes.
Yeah. So 4 plus 1 of time? You mean?
Yes.
Yeah.
Then it will be very convenient to just ignore the theta term.
But we don't live in a 4-dimensional space.
But
we certainly don't have the symmetries of a 4-dimensional space, which is what you would need to argue away the theta term.
we can just suppose it
well,
exists.
You can suppose, but it's not true. I mean, it's not. Well, you can suppose but you can't suppose that that's a description of the world because it manifestly isn't. But the world has 3 space dimensions.
I know. Well, we can just.
Okay.
Yeah, thanks the question. I remember just so commonly remember the definition of fundamental particles. You know, people ask what's the definition of fundamental particles, and the C.N. Yang and T.D. Lee they like to define fundamental particles in an opposite way. That they say that people certainly know what is molecule, what is atom. So particles that are not molecule, not atoms, are called fundamental particles.
No, but it goes. That was good in its time, but now we can do much better. I think,
right.
Because as I discussed in quite a bit of detail, the equations that govern what we now call fundamental particles, the quarks and the leptons and so on, are highly constrained, and their structure is dictated by deep symmetry principles that can't be changed. And so the fact that you have entities that are described by exactly those equations means their only fundamental properties are things like spin, charge, color. That's it. That's all you need to know. There's nothing more to be said about what these particles are. So what we mean by a fundamental particle is a particle that obeys these fundamental equations.
Okay. All right. Feng?
Yeah.
So in this lecture and the past several lectures, we are keeping talking about the phase. Without the phase, the whole theory just collapses. However, in the classical physics, in Newton equation or Hamiltonian equation, Lagrange equation, there's no phase. So in your opinion, what's the fundamental reason to cause this huge difference?
Well, that's a really deep question and a very, very interesting one. I'm not sure I can give an adequate answer off the top of my head. But, well, the world is described by quantum theory. And in quantum theory, we have a connection between conservation laws. Well, also in classical theory, we have a connection between conservation laws and symmetry. But in classical physics, we don't have symmetries associated with things like conservation of number. We don't. There's no symmetry associated with conservation of any particular chemical element or baryons. But in quantum mechanics, we do have a symmetry that's associated with conservation of number, and it's rotation of the phase that's conjugate to that number. And I don't know whether, that's a profound new feature of physics introduced by quantum theory that really, I don't think has a classical analog. I mean, yeah.
Yeah, that's a very deep question. More questions?
I mean, you can introduce chemical potentials, of course, when you have conserved quantities, and that's sort of related, but it's not a phase, it's just a number. Yeah, I don't know.
Hi, Frank. Thank you for your wonderful talk. So I have a maybe naive question. So I wonder what's topology in topology in high energy physics because I'm from condensed matter physics.
Yeah.
And when we talk about topology in condensed matter physics, we talk about Bevel curvature
Yes.
or Chen number, and it turns out that the conductivity of the material is quantized.
Yes.
And we call this topology. And I wonder, what's topology in high energy physics?
Well, topology has several applications in high energy physics, but the one that's relevant here, which is probably, in my opinion, maybe the most important one, is you have non-abelian gauge fields. So they're gauge fields that, if you like, live in a space that's pretty complicated. That's in the case of SU3, it's an 8-dimensional space, and it has structure. It has, and if you can have field configurations which explore that structure. So they wrap in that space. Has non-trivial topology. It actually has the topology of a 5-dimensional sphere glued to a 3-dimensional sphere or something like that. And so you can wrap around those spheres. That's the basic. Right, so the fields move around. You make gauge transformations which explore the space. And they can be globally trivial. I'm sorry, locally trivial, but globally non-trivial because you explore the full range of the group.
Okay, thank you. So are there some physical observable about this topology, or is just some structure of the?
Well, particle physics is kind of impoverished as in the experiment, the direct experimental access you have to its degrees of freedom. You know, the classic particle physics experiment is you bash particles together and see what comes out. So, you know, there's not any obvious topology in there. So a lot of interpretation goes into it, which is what we've been discussing here. But you derive consequences from the deep theory that are reflected in the experiments or not, and that's how you infer that if your description is successful, you infer that that's the right thing. Now what you can do is numerical experiments, particularly in QCD, and you can explore you can see vacuum fluctuations, you can see the dynamics of gluon fields, and you can see the fields exploring these spaces. So you can actually see topology pictorially if you look at the right thing in numerical simulations of QCD. So it's very, very, that in numerical experiments is very concrete.
Right, Frank. So maybe I ask the same question in another way. So I guess the chance question is, in condensed matter physics, okay, first of all, when we talk about topology, it usually links to some integer number. So
yeah, by the way, it's usually topology in momentum space. So it's also pretty abstract.
Right, can also be in real space. But anyway, the topology always links to some integer number. And in condensed matter physics, when you say some materials has some topology, usually you can see the conductance is quantized.
Yeah.
And that quantization number directly, it is discrete. So it directly links to the topology. Yeah. And in high energy physics, in particle physics, do you have some experimental observables that is kind of integer that links to topology?
Yeah. Well, it's in the case of these the gauge fields, when you have topologically non-trivial background gauge fields, then you get zero energy solutions of the Dirac equation, these zero modes, and those are integers. The number of left minus right solutions is an integer that reflects the topology directly.
Right.
Yeah. So, and that gives you discrete changes in quantum numbers that otherwise would be conserved.
Oh, I see.
So yeah, it's a very well. So it's if you could actually, if you could access those degrees of freedom experimentally, it would be
Right.
very direct.
Right.
And you can access them very directly in numerical experiments, but laboratory experiments
I see.
need a lot of interpretation
I see.
to
I see.
bring that. Yeah.
Right. Maybe in.
Yes.
Yeah. Okay. Ziang.
Hi, Professor. Could you turn the PowerPoint back to the maybe the musical map cap illustrate the spontaneously symmetry breaking?
What is it you wanted to see?
The Mexican hat.
Oh, the Mexican hat.
Yeah.
Right. This.
Maybe it's about some confusion in my listening. Do you mean that some the states evolve with time?
Yes.
So is there some precise mathematical form of this evolution?
Yes, we'll discuss it next time. I just ran out of time, but yes, we will derive the equations of axion cosmology, which are very much simpler than the anomaly analysis, and very, very interesting and instructive, and we'll absolutely do that. Yeah.
Okay, so is it corresponds to the evolution with time when conducting a phase transition, the process of a phase transition?
Well, not really. The phase transition occurs, and you get a vacuum expectation value for this field. This is about what happens after that. Okay. Well, I could have drawn the picture. I mean, yeah, this is what happens after that. You can discuss what happens before that too, but it's different. And since we're interested mostly in what happens at the very end, this is a good place to start.
Oh, so it's not about the phase transition.
It's not about the phase transition. It's about the aftermath of the phase transition as the universe expands.
Okay. Because when you talk about this, I just think when it evolves with time, and we can do a precise mathematical form to describe it. But when do research in phase transition, there's always what phase in a specific condition, but not how to one phase evolve with time to another phase. So
yeah, the description of the dynamics of phase transitions can be quite complicated, and depending on the details of the physics that governs the phase transition. This is much simpler.
Okay.
Yeah.
Thank you.
Okay.
Okay.
Oh, there's another one here.
Hi, Frank. I have a very naive question, I think. So it's about, I remember that the Noether theorem only holds for global transformation.
For global transformations.
Yeah, but
yeah, well, yes, the classic Noether theorem concerns continuous transformations, and we discussed before how the picture is modified when you have gauge fields involved. So the spirit of the argument is the same, but the conclusions are different because the equations are different. But when you apply the same reasoning to the different equations, instead of a massless boson, you get a massive vector particle and superconductivity. Instead of superfluidity, you get superconductivity. But it's really the same thing.
So you still can use that theorem to derive.
Well, you can use the spirit. I mean, it depends what you call the theorem. But if you use the algorithm, you can discuss both in the same terms.
So the axiom.
The right way. asymmetry is actually never broken. The usual theory you'll find in textbooks is not quite adequately, not quite carefully correct stated. The careful statement have spontaneous symmetry breaking and the spontaneous symmetry breaking theory by a small gauge coupling, then you get a mass vector particle instead of a massless scalar. But
thank you.
But it should not be your gauge symmetry. It's not. That's not. It's just you couple a gauge field weakly to a spontaneous symmetry breaking.
Yeah, that's true. I read a lot of books and also confusing in that point.
Yes. So I've.
Okay.
I probably should have kept my mouth shut, but that's an interesting story.
Thank you, Professor. My question is there any competitive solution to solve the strong CP problem besides the axions?
There are discussed in the literature various other proposals, but I wouldn't call them competitive. I mean, they have not won the allegiance of very many people, including their authors in most cases. I think consensus can always be wrong, and there might be other bright new ideas that are going to come later. But so far, this seems to be the way to go. Yeah.
Oh, okay, I see. Thank you.
Okay.
Hello, Frank. A very nice talk and an interesting theory. So my question is, so as we all know, the extreme astronomical phenomena like binary neutron star merger, this is a playground of nearly 4 interactions: the strong, the weak, the electromagnetic, and the gravitational. So will the multi-messenger astronomical observation of such event may contribute to the measurements of axion properties, like their mass and their distributions?
It's an interesting question. I don't think so, but it could be it could be an interesting thing to investigate carefully. I mean, those events are so complicated; they're not on the face of it. They don't seem like promising hunting grounds for weak interactions, but it's not entirely impossible, I guess.
Okay, thank you, Professor.
Okay, more questions? All right, so we already have a lot of questions. So maybe let's conclude today and see you on Saturday, right?
All right.
Yeah, Frank.
Good.